Hi, here we discuss about a project ECG signal to spectrogram HEX conversion and HEX to spectrogram ECG reconstruction for VLSI based arrhythmia classification. In this work, a MATLAB based graphical user interface or GUI has been developed for converting a single lead electrocardiogram signal into spectrogram images and hexadecimal data suitable for hardware deployment. The primary objective of this framework is to support VLSI based hardware classifier, particularly convolutional neural network and gate recurrent unit architecture for arrhythmia detection. The generated spectrogram HEX files are designed to function directly as a memory initialization data for on-chip image classification system. Now we can verify the block diagram. So this block diagram illustrated in figure 1. Here the complete workflow of the MATLAB GUI based ECG spectrogram HEX converter system. This architecture is divided into two major sections, the forward path and the reverse path. In the forward path, the process begins with ECG MAT files contain a time, millivolt and voltage signal information. So this system first press and decode the time domain ECG data. After decoding, the user select a specific ECG region of interest, typically represented in millivolt. Next, the selected ECG segment undergoes detrending to remove baseline, drift and unwanted low frequency component. The cleaned signal is then transformed into a spectrogram using a short time Fourier transforms or STFT. It's producing a time frequency representations of ECG signal. The generated spectrogram magnitude is converted into decibel scale values using a 20 log base 10 of the signal magnitude. So these values are then normalized between a 0 and 1 to standardize the image intensity range. After normalization, the spectrogram is resized into 256 x 256 image format suitable for hardware processing. The resized spectrograms is mapped using the jet color map to generate a full RGB image representation. The RGB image is then separated into red, green and blue channel individually. So these channels are converted into the hexadecimal values and written into the separate hex files together with the metadata headers required for reconstruction. Finally, this GUI displays the generated spectrogram using the jet color map visualization for user verification analysis. Okay. The second section represents the reverse path. Okay. So where the stored hex files are used to reconstruct the pseudo ECG signal. The process starts uploading the 3 RGB hex values into GUI. The system feeds the hex data and extract the embedded metadata information. Using this information, the original 256 x 256 RGB spectrogram images is rebuilt. So next, the inverse jet color map processing is applied to estimate the original grayscale spectrogram magnitude. The image is resized back to its original spectrogram dimension, followed by denormalization to recover the original decibel values. This decibels magnitude values are then converted back into the linear magnitude form using the inverse logarithmic relationship. Since the phase information is unavailable in the stored images, the fast Griffin-Lim algorithms is employed to iteratively estimate the missing phase component. After phase estimation, a custom overlap add based inverse short time Fourier transforms will reconstruct the time domain waveform and the signal is rescaled and phased through ECG polarity corrections to ensure the proper orientations of the waveform, especially the orbic direction. Finally, the reconstructed pseudo ECG signals is plotted and displayed to the user. Now we can verify the output. Okay, so here we have used 3 different GUI for VLSI design and testing spectrogram based ECG project. First GUI, ECG to spectrogram with spectrogram to ECG in same GUI. Okay, so this one. So this is a MATLAB code for this process. Okay, now I'll run this code. Okay, so here you can verify the GUI. Okay, now I'll upload the ECG signal. So this ECG signals, it will be recorded from MIT BIS database. So here we have chosen for different number of arrhythmia datasets. It will be cover 100 to 232. Okay, so it's all the values that will be given in the decimal values. Okay, so here you can verify that in Vim. Okay, so here this is a value, here this is a value. Okay, so these values will be plotted in the waveform. Okay, and here you can select a ECG wherever you want. Okay, so now I'll given a select region to choose the region of number of ECG signal. So if you need only one ECG signal, you can select only one, or how much you are needed, you can select it. Okay, so maximum size of the ECG signal we can possible to select, it's 6. Okay, so now it will be given and export to spectrogram. Okay, so once the spectrograms it will be generated, it will be show the pop-up exportation done. Okay, so now we can verify the hexadecimal file spectrogram R, spectrogram G and spectrogram B. Okay, so this is the hex values. Okay, so now we will upload the spectrogram hex values. Okay, so we can use this image and we can use this hexadecimal file for encryptions or anything. Okay, after the process of decryptions or something, okay, we will use the same hexadecimal file here, upload spectrogram hex values and spectrogram R, spectrogram G and spectrogram B. Now it will convert again, which means it's a reconstruction process happen, and it will be presents the same ECG signal. Okay, but little bit difference it will be came. Okay, why? Because it's approximate one. The next GUI is ECG to spectrogram and hex conversion. Okay, so here you can check the spectrogram output and the hex values. This one, here you upload the ECG data. Okay, and select the region. Okay, so now the spectrogram data will be converted. Okay, and now we can analyze as the hex values. Okay, so here you can check the hex values. So now you choose a 101. So 101 RGB it will be created. Okay, so these are the hex values, G value, okay, and B hex value. Now we'll check for next GUI, hex to spectrogram and ECG reconstruction. So this one, here we upload the RGB hex files. Okay, and it will convert the spectrogram images. After that we can choose the ECG reconstructed data to hexadecimal file. Okay, so we can choose 8-bit or 16-bit, whatever you are needed, you can choose it, and it will be exported. Okay, so once exported, you can check the hexadecimal files in the work folder. This one, so here you can analyze the hex value. Okay, so this hex values we also plotted in a modelism tool with support of the VLSI code. So this is a VLSI code, so we use the same file here and we just plotted the value with support of file reading. Okay, now I will show the modelism output. Okay, so this is a simulation result. Here the same ECG signals that will be plotted, so we can use this ECG, we can find out the arrhythmia classification. Okay, and here we updated the document in all details. So forward path, reverse path, GUI layout and working principle, Okay, all the details notes we are given here. Okay, can verify that all the documents. Okay, and finally we cover with the conclusions and reference also. Okay, thank you.
Introducing Nxfee Innovation, your trusted partner in IP design and VLSI research. With over 300 plus completed projects in cutting-edge domains like low-power VLSI design, high-speed data transmission, signal processing, and secure networking, we offer tailored solutions for students and professionals in BE, BTech, ME, MTech, and PhD programs. At Nxfee, you not only get expert-guided projects starting from RIS 6000 Transparency, but also enjoy unmatched benefits like RIS 1000 off on your second project, free documentation, and easy-to-understand video explanations. Plus, our rewarding referral program lets you earn up to RIS 2000 MANTs for every successful referral. Trust us to simplify your research journey with high-quality, affordable, and fully customized VLSI solutions. Visit our website to explore a comprehensive collection of projects, organized year by year from 2014 to 2024. The latest 2024 research projects are now available for publication, along with several 2024 non-completed titles, which are updated monthly with new possibilities. For application-based projects, interface designs, and mini projects, you can also rely on Nxfee for top-quality solutions. We provide exceptional PhD assistance with full publication support and offer an installment payment option, allowing you to pay module by module. Let Nxfee guide you through your research journey with flexibility and expert support. Thank you.